Hello students, welcome to lecture 2 of the online course on Introduction to Microwave and Optical Metamaterials. So, here is the lecture outline. We will briefly look into the applications of microwave metamaterials, which we could not cover in details in the previous lecture. We will revisit metamaterials, some fundamental concepts again, and then we will move on to optical metamaterials. We will discuss some interesting applications of optical metamaterials, including optical negative index materials, optical magnetism, and metalens. So, we have seen that in metamaterials, the meta atoms play the most critical role. So, the design of the meta atoms and their overall arrangement in the form of an array can make it possible to achieve medium parameters with extreme values such as 0 and negative. Either it can be permittivity or permeability. Also, you can design materials with high anisotropies and inhomogeneities. So, when we talk about microwave metamaterials, they are basically working in the range of megahertz to 100 gigahertz. And the most unusual physical phenomena were first demonstrated at the microwave frequencies. As I mentioned, it is easier to perform experiments in this particular frequency range because of the dimensions of the meta atoms, which will be typically in millimeter range. Okay. So, the effects like negative diffraction, which we discussed briefly in the last lecture, were shown using complementary split ring resonators along with wire arrays. Okay. So, this was a metamaterial which showed the first negative refractive index. It was also designed in the shape of a wedge. So, this was a negative index wedge. And what happens when you have negative index? So, the conventional material, when light falls from vacuum to this material, it will just bend a little bit, but it will be on the other side of the normal. So, that is the typical refraction that we know. But when you replace this conventional material with this metamaterial, which has got a negative refractive index, so the light or the electromagnetic wave will bend on the same side of the normal and it will go in this direction other than going this way. So, this is completely unusual physical property of any material. Other applications include invisibility cloaking. So, here you can see in the normal propagation, you have a microwave source and there is a solid object which is being visible because of the reflections from the object. Okay. But if you want to keep this object hidden from the microwave source, you have to think of a cloak that is made of metamaterial. So, here you can think of a cloak which is basically rings of the split ring resonators. Okay. So, here at least you can see theoretically that light rays can bend around this solid object, okay, inside the cloak, and this is how you can make the light rays appear as if there was no object standing here, right. So, this is another illustration of the ray tracing program that has been used to calculate the ray trajectories when you have a object which is being surrounded by this particular cloak. So, here you have to remember that this R2 is much greater than the wavelength of the light we are talking about. Okay. Then when you realize this using metamaterials, this is typically how a two-dimensional microwave cloaking structure looks like. Okay. So, here you have the plot, okay, and you can see that mu r, which is basically shown in red, that is multiplied 10 times for the clarity, whereas you have mu theta. Okay. So, mu theta is basically the green one, which is having constant value of 1, and epsilon z is the blue one, which has also got a constant value of 3.423. Okay. So, here what is shown that you have basically rings of split ring resonators lined up. So, this is the structure of the split ring resonator in the inner array, and this is how it looks like in the outer array. Okay. So, what it does, it basically guides your rays like this around the object. So, whatever you are putting here in the center is basically getting hidden, right. So, this is another snapshot from the time dependent study. So, here you can see these are the electric field patterns with streamlines indicating the power flow, that is the Poynting vector. So, here this is the object that is being hidden by the cloak. So, what was the line, the way the wave was propagating because of the cloak, after that also it propagates in the same way. So, you will not be able to see this object, right. So, it is basically the invisibility cloaking. So, invisibility cloaking is possible because of the metamaterials, where you will have the requirement of some extreme values or exotic values of permittivity and permeability. So, in this particular course we will go into the depth of understanding transformation optics and other concepts relevant to invisibility cloaking, and we will show you how to design those kind of metamaterials. Okay. Now, moving forward, there are other applications like optical illusion. So, here you can see a golden apple, which is the actual object enclosed within a illusion medium, the blue one, okay, and in the physical space. So, what happens, it will behave as if there are like two green apples in the virtual space. So, if you think, in other words, the tangential components of the electromagnetic fields of the whole virtual boundary, that is S2, will be exactly same in the physical and the virtual space. So, here and here the overall effect will be similar, and that is how you can match it. So, in this particular diagram you can see that if you have an object like this, okay, in the path of your electric field distribution, you can see this, but when you put this within this particular illusion medium, so what is inside, this is basically a metallic square cylinder, and you are putting it within this illusion medium layer. So, it behaves like as if there are two objects, okay. So, it is creating the same effect as if there are two dielectric square cylinders, okay. So, that is how also you can create an optical illusion, okay. So, instead of having a golden apple, you can think of having two green apples, something like that. So, here are the application trees of metamaterials, okay. So, you can see discovering the new physics has become undoubtedly the most necessary kind of requirement for developing all this new metamaterials, okay. So, if you think of effective medium metamaterials, okay, you can design RF components, antenna radomes, RCS reduction, and different new antennas based on that, right. So, these are some key devices and components that are typically unavailable with the traditional techniques, but using effective media metamaterial you will be able to design those. When you come to plasmonic metamaterials, a new surface plasmon polariton based framework for microwave technology can be set up, from the basic transmission lines to systems, and also in the integrated circuits, which not only compensate the traditional microwave technology, but also produce new and irreplaceable applications. Okay. So, here you can think of creating different active and passive devices, localized surface plasmon resonance, different types of waveguides, okay, integrated circuits based on plasmonic metamaterials. Okay. There are metamaterials which can be also used for digital coding. Okay. So, those are also called information metamaterials. So, they have huge potentials, as you can expect. So, naturally the digital coding metamaterials will evolve to be the software defined and even cognitive, from being reprogrammable, leading to information metamaterials such as all these different types of tunable structures. So, Information metamaterials will represent a link between the physical science and new information science, which will result in many new concepts in the information systems. So, in the future, all this belongs to microwave metamaterials. They not only represent a material or a device, but also an overall intelligent system or real time information processor. So, what we have seen till now, that almost all electromagnetic phenomena and devices, they basically result from the interaction of electromagnetic waves and materials. And in this particular sense, the realization of the electromagnetic functionality, that is, the desired epsilon and mu, permittivity and permeability, is meant to manipulate the way waves are going to behave with your structure, and you can manipulate the interaction, right. So, with the myriad of delicate structures proposed and produced by the scientists and engineers over the over last 1 decade or 1.5 decade or so, the eventual capacity and diversity of the electromagnetic devices, okay, have largely increased, because they are not only restricted by the available materials, as we have seen in the previous lecture. So, some fundamental constraints do exist that may make some desired properties absolutely impossible, but then more or less, without those extreme features, you can right now achieve good amount of desired properties using the metamaterial concept, right. So, few things are not possible, as I mentioned. Say no medium can allow a chain of optical pulses to travel at a speed faster than the speed of light in the vacuum, because of the causality requirement. Okay. However, there are many other desired electromagnetic properties, something similar to the case of monopole magnets seem to be lacking in nature, but there are no physical laws that basically prevent from such phenomena to exist. So, those kind of things you can try build in this metamaterial world. So, if you revisit the metamaterial concept, you will see then it is an approach to realize a novel electromagnetic property, okay, from the artificially structured composite. And for that, what is important, that you are basically making some functional inclusions in a proper arranged manner, and those inclusions are typically sub-wavelength in dimension. So, although the unit cell size are several orders of magnitude lower than the wavelength, okay, and they are beyond the atomic and the molecular level of a conventional material, the inhomogeneity scale of this kind of composite structures is still much smaller than the wavelength of interest, and their electromagnetic responses can be, although the unit cell of such inclusions is usually several orders beyond the atomic or molecular level of a conventional material, the inhomogeneity scale of these composite structures is still much smaller than the wavelength of the light or electromagnetic wave of interest, and their electromagnetic response can be expressed in terms of homogenized effective material parameters. Okay. So, here you can see that these are the red dots show the inclusions. So, this is where the diameter is much larger than lambda. Okay. So, as you go this side, okay, your wavelength is increasing, or you can say the inclusions are getting much smaller as compared to lambda. Okay. So, in that case, when it goes like that, your wave is not able to resolve the internal structure of the material. So, from here things are getting just diluted, right, because the feature size of the inclusions are much smaller than the wavelength. So, wavelength cannot resolve those. So, you will start seeing a more or less average homogenized property. Okay. So, that is why from the initial red colors, which shows some properties of the inclusions, if you keep moving towards the right, you are seeing that you are basically getting a light red color, because things are just getting mixed up somewhere mixing between the red and the white, and you will see that for d greater than lambda by 5 you are getting more like a homogenization picture. So, this artificial and functional materials engineered to fulfill the prescribed electromagnetic properties, and these are called metamaterials, right. So, with the platform being set up right now, let us introduce and focus on another aspect of metamaterials, which are carefully fashioned structures to exhibit exotic properties at the optical frequency domain, and those are typically called optical metamaterials. So, when tracing the history, people started using optical metamaterials deliberately in art pieces without even having full understanding of the physics that resulted in those exciting features. A famous example is the Lycurgus cup that is still in display in British Museum. So, there the Roman, it is a basically Roman glass from 4th century AD. So, you can see that this cup was made from probably the first known metamaterial, that is having ruby glass with gold nanoparticles embedded. So, when you shine light from outside, the nanoparticles scatter the green light. Okay. So, you can basically the cup appears green, but if the light source is inside, okay, those nanoparticles, they basically absorb the blue green light, and what is coming out to you is basically the red light, and that is why the cup appears red. So, the same cup looks different because of this nanoparticles being embedded with the glass. Okay. So, the idea of metamaterials has been quickly adopted by the optics community. Among all the branches of today's metamaterial research, you will see that the materials which can exhibit tailored electromagnetic responses at optical frequencies, they are very fascinating and they are most challenging as well, and this is the domain of optical metamaterial, right. And light is the ultimate means of sending information that we have learned. Okay. So, anything you can send with light, because it can package data in a signal of zero mass and unmatched speed. So, people are always fascinated about what they can do with light. Okay. So, with the amount of optical metamaterial research activities going on, and with the combination of continuous improvement in the nanofabrication technology, there are a lot of advancements made in nanoscale imaging and computational electromagnetic design and simulations. All these things together have made this field a very attractive one. So, this is one example of a broken symmetry metasurface, which is made of cuboid kind of resonators. So, you see the incoming light has got a broad spectrum, you see here, but after passing this metasurface, the beam becomes very spectrally narrow. You can see the blue sharp resonance. Okay. So, here what is happening, the swirling patterns that you can see, the swirling patterns of the arrows shows the electric field distribution of the light trapped in these dielectric resonators, and that is what is giving this kind of a sharp transmission, okay, narrowband transmission. So, these are new features that can be designed based on the metacell, which was the cubic resonator in the previous case, and their arrangement. You can put them in square lattice or any other lattice, okay, and accordingly their spacing can be controlled so that the properties can be controlled. So, within this rapidly developing and highly multidisciplinary field of optical metamaterials, there are several interesting research directions, such as optical negative index materials, optical magnetism, Metalens, giant artificial chirality, electromagnetic cloaks for invisibility, and imaging. These are gaining a lot of attention, right. So, here is a bird's eye view of this entire field of optical metamaterials, which is also known as meta optics. So, the fundamentals tells you that you can have control over the polarization, amplitude and the phase of the reflected or the transmitted light. Okay. You can make devices such as monochromatic or achromatic Metalens. Okay. So, they can be flat lens with perfect resolution. We will discuss how they looks like. You can also think of vortex Metalens, and they can be used in applications like edge enhanced imaging, image progress, computational imaging and so on. Okay. So, let us pick up one by one. So, if you think of optical negative index material, so you can use a double periodic array of pairs of parallel gold nanorods. Okay. Here you can see the polarization current goes this direction and opposite in the other gold nanorod. So, this can give you negative refractive index at the optical range. So, for light normally incident with electric field polarized along the length of these rods, and you can maintain the magnetic field to be perpendicular. Okay. You can see that the electric and the magnetic resonances both experience resonant behavior at certain frequencies, right. So, this is how the schematic looks like for this array of nanorod pairs. This B shows the FEM or the field emission scanning electron microscope image. So, this is the length scale 5 micron, and this is the length scale here when you zoom it further. Okay. And this is how the elementary cell looks like. Okay. So, such behavior of having electric and magnetic resonances from the plasmon resonance in the pair of nanorods can give both electric and magnetic components. Okay. Or such behavior results from plasmon resonance in the pair of nanorods for both electric and magnetic components of light. So, when we talk about plasmon resonance, we are basically referring to surface plasmon resonance, which is a phenomena that occurs where electrons in a thin metal sheet becomes excited by light, is directed to the sheet with a particular angle of incidence and then travel parallel to the sheet. Okay. So, when the experiments were done, they could see that a negative refractive index, basically the real part n prime, was found to be minus 0.3, and this was achieved at the optical communication wavelength of 1.5 micron, right. So, here is the real n prime is the real part and n double prime is the imaginary part of the refractive index, which is obtained from the simulations, and this is you see from the experiments. So, these ones are the simulation and the circles are basically the experiments. The zoomed version shows that you are actually getting negative refractive index at a particular range, wavelength range. So, at 1500 nanometer, n prime was recorded to be close to minus 0.3, right. So, you are actually able to create negative refractive index at a particular wavelength based on the design of a unit cell, which looks like this. Okay. The next important or interesting application is optical magnetism. Normally, all the materials are non-magnetic at optical frequencies. So, mu r equals 1, but you can actually have optical magnetism, right. So, optical negative index metamaterial or NIMs, which are also known as left hand materials, are basically artificially engineered metal dielectric composites that gives you n prime negative over a certain range of frequencies, right. In addition, a magnetic resonant behavior should be also observed for these negative index materials at this range. So, the magnetic resonance in any optical negative index material is always required to make the real part of the effective refractive index negative. So, for that, either you have to have this condition that your mu prime is negative or your epsilon prime is negative, or you can follow a more general necessary condition, which is this one. So, epsilon prime mu double prime plus epsilon mu prime epsilon double prime should be negative. So, this is valid for a passive medium. So, always remember single prime denotes the real part of the permittivity or permeability, and the double prime tells you about the imaginary parts. Okay. So, how people have actually realized optical magnetism, you can see from this figure. So, yeah, they have taken pairs of thin silver strips this time. So, these are the two silver strips which are separated by a dielectric spacer alumina. Okay. This offers an easy way to achieve negative magnetism by coupling the near field modes. So, here you can see the thickness and the width of this, and the strips is separated by alumina layer of thickness D, which is width is again W, and the refractive index is 1.62, and that there is no image complex part, okay, image 1.62, and you can consider this in the form of a sub-wavelength lattice constant or a grating. You can consider this as unit cell in a periodic grating, 1D grating. So, this P is given as 300 nanometer, okay, and these are the other parameters, T equals 35, D 40, and W equals 140 nanometer, right. And they have considered resonant TM polarization. So, in that case the magnetic field is aligned with the largest dimension, that is along the infinite length of the strips. Okay. So, in such a case when you study the response, okay, you can plot the epsilon prime and mu prime for this particular structure, okay, and you see that mu prime gives you negative magnetic response in the TM regime, and it extends from typically 720 to 825 nanometer. And this particular figure shows you the cross section of the structure adjusted related to the actual structure when you try to fabricate it. So, it gets bit of tapered, but more or less you get similar kind of response. So, the last important application that we will be discussing today will be of Metalens. So, what is Metalens? First you have to understand that making a perfect lens that produces flawless images have always been the dream for lens makers for centuries. So, in 1873 Ernst Abbe could discover the fundamental diffraction limit in object. So, that tells that whenever an object is imaged by an optical system such as a lens of a camera, fine features which is smaller than the half of the wavelength of light lambda by 2 will be permanently lost in the image. So, this loss of information arises from the object's fine features because they carry high spatial frequency, that is they are evanescent waves, basically decay exponentially, and that is why you get an imperfect image, because those waves cannot be captured. So, the lost treasures such as these sub-wavelength details are the fundamental reason for Abbe's diffraction limit, which determines the smallest feature that one can see through the best of the lenses. So, practically speaking, this limits the resolution of all the imaging and the lithography systems, which are the cornerstones of the modern biology and electronics. So, that was the big challenge, and metamaterials helped us to overcome this hurdle. So, for more than a century, a lot of attempts have been made to overcome the diffraction limit. In 1967, Vassalagor raised the question of the physical meaning and feasibility of these hypothetical materials with negative index of refraction, right. So, he could see that in a negative index media, a number of surprising phenomena occur, such as reversal of Snell's law or the Doppler shift. Doppler shift is nothing but change in the frequency of a wave in relation to an observer who is moving relative to the source of the wave, right. I believe all of you know this. So, this new phenomena, this reversal, do not violate the law of physics, but they are pretty challenging to realize, and they are counterintuitive, right, and physical perception is also a bit difficult. But if you put a negative refraction, if you want to see negative refraction at the interface between a positive and a negative index medium, okay, so that can be done by just putting a negative index material here, and you have air on both sides. So, you see light enters, and because of negative index it comes this side, and you can focus all the diverging light beams. So, these two beams are basically diverging, but because of this negative index media you are basically converging them here. So, you can actually form two images, one inside the slab, one outside the slab, right. So, all the beams can be now captured, and that can give you a perfect image, right. So, the light emitted or scattered from an object includes not only the propagating waves, but also the evanescent waves that carry the sub-wavelength details of the object, right, the high spatial frequency components. Now, that is what our main problem was, that the evanescent waves decay exponentially in any medium which has got a positive refractive index. So, they were not being collected by the conventional lens, and that is what was resulting in the diffraction limited images, right. But if you think of a lens which is basically made of this negative index medium and it is placed close to an object, so what happens, the near field evanescent waves, okay, which were basically decaying, now gets enhanced, okay, it was exponentially decaying, so now they get enhanced, and then further when they decay they basically come to the same level as they were in the object plane, right. So, the amplitude of the evanescent wave are found to be identical at the object and the image plane, and that is what is amazing, because when that happens you are basically, because of this NIM lens, the evanescent waves, okay, come at the same level and you can capture that, right. So, the propagating waves will also pass through this, okay, and when you have both negative refraction and reversed phase font, you are basically leading to a zero phase change at the image plane, right. So, by completely recovering both the propagating and the evanescent waves in phase and amplitude, you can create a perfect image, and this is the schematic of an microscope based on ideal negative index medium lens that should focus both propagating and evanescent waves into an image with arbitrary high resolution. So, thank you. That is all for this lecture. If you have got any query, you can always drop an email to this particular email address. Thank you.